So if you're upset with your mark, then hey, you're allowed to be upset with your mark. That's totally fine. But let me know how I can help. And if I can't help, then I don't know. I guess it's incumbent on you to try and figure out how to do better next time. If you're happy with your mark, then I'm happy with your mark. No problems. We are looking at our 15.2 Le Chatelier's principle. Does this idea of adding or taking away something and then the equilibrium shifting to either use it up or replace it, does that idea kind of make sense? Yeah, like for example, I'm going to do a brand new, whatever, it doesn't really matter, okay? So A plus 2B plus 40 kilojoules, I don't know, whatever, it doesn't matter. It's turning into 5C, whatever. So let's take a look at this expression or this reaction. If I added B, if I added more B here, what would happen to our equilibrium? Would it shift to the left or to the right? If I add B, the equilibrium is going to shift in a way that opposes what we just did. So if we added B, the system's going to use it up and turn it into C, right? So immediately, what happens? What's the first immediate change to any of these concentrations? What did you do? What did I do? I added B. So immediately B is going to increase, right? Now, because I increase B, the equilibrium shifts to the right. Well, what does that mean? What's going to happen to all of these concentrations? Slowly over time, what's going to happen to the concentration of A if we shift to the right? It's going to decrease as a response. What's going to happen to B? It's going to decrease by double the amount because it's got a coefficient of 2, okay? And then, temperature, whatever, we can't really graph that as a concentration. It's not that big of a deal. What's going to happen to C? It's going to increase by 5 times this amount, right? So it's going to increase. But all 3 of these changes happen gradually, and they all happen at the same time. Does that make sense? As we're turning this into this, these go down, this goes up, and it happens at the same time, at the exact same, slowly over time. We're going to continue on this idea. We're going to continue on this idea of taking a look at changes in concentration to assess Le Chatelier's principle. We're going to do the very last one, pressure and volume. Pressure and volume are related to each other. Would you agree? If I change the volume of a container, then the pressure inside that container will change as well. Hopefully that kind of makes sense. I've got a little bit of a demonstration, not a demonstration, just like a visualization over on the side here. So I've got a container, and the container has a piston on the top. You guys know what a piston is, right? No? Like a plunger. A piston or a plunger or what? Okay, that's fine. So all this means, this is because it's a piston, it can move up and down, right? So if I took this piston and if I lowered it, what would happen to the volume of the container? Would it increase or decrease? It would decrease. Okay, so let's do that. Now, as I take this piston, right, and as I lower it, what happens to the concentrations of all of these particles? Okay, don't say anything out loud. Do the concentrations increase or do the concentrations decrease of all these particles? Don't say anything out loud, okay? So as I'm decreasing the volume, right, as I'm decreasing the volume, what's happening to all these particles? Did their concentrations increase or did they decrease? What do you think? Did they get closer together or further apart? They got closer together. What does that mean? Does that mean they're more concentrated or less concentrated than they used to be? They're more concentrated, right? Also, now that I've pushed this plunger all the way down to here, this piston all the way down to here, what's the pressure in our system like? Is the pressure higher or lower than what it used to be? It's higher. Why is it higher? Because all the particles are closer together. Would you agree? And when things are closer together, there's a higher chance that they're going to bump into each other. And that's what pressure is, right? Pressure is these particles colliding with each other and colliding with the walls of the container. Okay, all right. So by decreasing volume, you increase the pressure. But also by decreasing the volume, you make things more concentrated. Did just the blues get more concentrated? Or did the reds get more concentrated as well? Well, do you think everything in here would get more concentrated? Yes, I think so. I think everything would get more concentrated. Now, I do want to bring up something. Okay. So let's say we had a liquid in here. I'm curious, are liquids compressible? Can you compress a liquid? You can't. You can't. Not to any appreciable extent. Not to any appreciable extent. That's the reason why hydraulics work so well, right? If anybody's in automotives, right? You have hydraulic lines running all over your car, like brake lines and things like that. And so those hydraulic lines, they're filled with fluids that are liquids. And so when you push on a liquid, it doesn't compress, so it gets pushed somewhere else.
Can I just ask a question? Why can you compress a solid?
You can't. You can compress a solid only if there are gaps in the crystal structure.
Oh.
If there are no gaps in the crystal structure, you can't compress a solid. And liquids, because of their ability to move around, you can't compress.
Okay.
Because there are no, by definition, there are no gaps in it. Yeah. Okay, so let's do this. So if I compress this, right? If I compress everything here, if I decrease the volume all the way to here, did the concentration of my liquid change at all? You didn't change the concentration of your liquid, right? So pressure and volume changes only affect gaseous systems, and that's because these particles can be pushed closer to each other. They can be compressed. An increase in pressure will cause the system to shift to the side with the least gaseous entities. We'll talk about why that is here in a little bit. A decrease in pressure will cause the system to shift to the side with the most gaseous entities. Remember that a change in volume may cause a change in pressure the opposite way. Okay, let's try this. Example number 1. What direction will the system shift if the volume of the container is reduced? What happens to the concentrations of particles? What happens to the concentrations of particles if we decrease the volume? Okay, first of all, are all of these gases? Yes, okay, so they can all be compressed, right? Or they can expand, whatever. If we reduce the volume of the container, what's going to happen to the concentration of hydrogen if we reduce the volume of the container?
Increase.
It's going to increase, okay? It's going to increase. But what I want you to do is I want you to draw 3 arrows below it. Why 3 arrows?
3 times 3.
Because its coefficient is 3. Okay? Now, if we decrease the volume, right? Every single concentration is going to increase. Would you agree? Every single one of these gases is going to get closer to each other. So we're going to put 1 arrow up underneath the nitrogen. Why only 1? Because the coefficient is 1. Okay. Now, is the concentration of ammonia also going to go up, or is it going to go down? It's going to go up. It got compressed as well. And how many arrows would you draw? 2. Okay. Now, let's take a look at all of the reactants and then separately all of the products. Where do you see a greater change in concentration? On the reactant side or on the product side? The reactant side. So basically what's happening is that's like saying we're increasing the concentration of the reactants. Which direction will this shift? It'll shift to the right. Does that make sense? It's the exact same thing. It's the exact same thing as what we were doing here. We're adding energy, we shift to use it up. Okay? Here, we're not adding anything, but all the concentrations are increasing, right? And so because all of them increase, we have to see where's the greater increase, where's the greater change going to be. So because we increase the reactants more, then we shift to the right. So this is going to be a little bit of writing, and I apologize about this, but immediately what happens to these concentrations? Every single one of them increase. Would you agree? Every single concentrations increase. So the concentrations of all of them, all the concentrations increased. Now, because our system shifts to the right, slowly what's going to happen? Because we shift to the right, slowly what will happen to the concentration of hydrogen? It'll decrease. We're using this up to make that. So the concentration of H2 will go down. The concentration of N2 will go down. The concentration of NH3 will go up. Is this the exact same process as what we were learning about yesterday? It's totally the same. You don't have to do anything, okay? Now, what's actually happening, what's really happening in this system is that by decreasing the volume, what happened to the pressures of everything? Did they go up or down? All the pressures went up. All the particles are closer together, there's more collisions means higher pressure, okay? Now, because you increase the pressure of the equilibrium system, the system will shift to the side where there's less molecules of gas. What would happen if we turned 4 molecules of gas into 2 molecules? What would happen to the pressure there? Let's take a look at if there was just 4 molecules in here. If I turned 4 molecules into 2 molecules, would that be an increase or decrease in pressure? A decrease. And that's exactly what Le Chatelier's principle says. If you increase the pressure, the system will shift to decrease it, right? But this is a trick. This is a way of always doing the same thing and always getting the correct answer. Let's do this one together. Example number 2, what direction will the system shift if the volume of the container is increased? Now, if I've got a bunch of particles in here, right? If I've got a bunch of particles and I increase the volume, what happens to their concentrations?
Decrease.
They decrease. They get further apart, right? So, because the concentrations decrease, I'm going to put down arrows. How many down arrows here? 1. How many here?
2.
How many here?
1.
How many here?
2.
Immediately, all the concentrations go down. Okay, stick with me. It's okay, all right, let's do this. Okay, all right. Which direction will the equilibrium shift?
Well, they're equal. Yes. They're gonna stay the same. It won't shift.
It won't. Are we okay with that? Do you see that? Where do we have a greater change, overall change in concentration? How many down arrows on the reactant side? 3. How many down arrows on the product side?
3.
Whoa! That's what I'm talking about. Which way will it shift?
So this.
Because there's equal numbers of molecules of gases on both sides of the reaction, you actually don't throw this system out of equilibrium. When you change the volume in this particular reaction, nothing's thrown out of equilibrium. The same ratios of products over reactants are remained. If I doubled all these numbers but doubled all these numbers, as long as there's equal amounts of both, 2 divided by 2 is still 1, so no change. Does that kind of make sense? Kind of? Okay. Okay. Perfect. What direction will the system shift if a metric buttload, that's an actual unit, of helium is pumped into the container? Okay. So we've got our equilibrium system. There's water down here, but nobody cares about it because it's not in the equation. Okay. Now, if I pump a bunch of helium into here, I've got the reactants. Maybe they're red. Sure. The products, maybe they're blue. It doesn't matter. I'm going to add helium into here. Do you see helium anywhere in that reaction?
No.
No. Okay, I'm going to add helium. I'm going to put a buttload of helium in here. Ugh. What happened? The pressure went up, but did we change the concentrations of anything?
No.
Are the red things colliding with each other more often now that there's helium in here? No. So what did we do?
Nothing.
Nothing. Nothing changes. Do you understand? The helium is inert. It doesn't react with anything. It's not reacting with anything in here, so there is no change. Because helium is inert, there is no change in concentration. Do you know what the 3 dots means? Therefore, no change in equilibrium. If that isn't the coolest thing you've ever seen, get out of my face. That's so good. So now you've learned how to do every single one of these. You've learned how to do every single Le Chatelier problem just because you're putting arrows up or down underneath things. How cool is that? Yeah, whatever. It's cool. Trust me, it's cool. There's a bunch of stuff, there's a bunch of graphing problems that I want to go over tomorrow. Is that okay? Now, okay. I want to get ready for a lab. This lab should take like 20 minutes. The lab should not take very long. Yeah, we've got 35 minutes left, but I want to do the lab, okay? Now, while you're doing the lab, I only want you to focus on the evidence. You don't have to do the analysis while you're doing the lab out there, but I just want you to focus on the evidence to support your ideas. And then when you're done the lab, then you can come back in here and you can work on it, okay? I'm going to give you time to work on the lab write-up tomorrow as well. Literally all I want to do tomorrow is I want to do a couple graphing problems. It'll take us about 10 minutes. And I want to give you some time to do a quiz. This quiz is all about Le Chatelier's principle. Putting arrows up, telling me what immediately happens, which way something shifts, and then what slowly happens. Is that okay? That's really all we're going to try and do, or all we need to do for the quiz tomorrow. That quiz is going to take 10 minutes, like max probably. So I'm going to hand out this lab, and it looks beefy, it looks big, but that's only because I'm giving you lots of space to write. You don't need lots of space to write, but I'm giving you lots of space to write. I'll give you 2 minutes. Nine, 10. Nope. Yeah, sure. Right, it's beefy, but that's only because there's lots of space. Okay, I'm gonna go get something just really super quick, and I will be right back. You just put it on the corner of this table, and I'll deal with it later.
What are you doing?
Okay, I'm not giving you a procedure, and I'm not putting you in lab groups. If you want, just be in a lab group, right? You've worked in lab groups previously when we were doing the dynamic equilibrium thing. Okay, the first, let's just kind of take a look. It says part 1 and part 2. So part 1 is these cobalt-2 complexes. This is a chemical reaction that's in equilibrium. Hi. Hi. I keep forgetting to bring money. I'm so sorry.
No, don't be sorry. It's okay.
Okay. Thank you very much for checking.
You're welcome. Thank you. Don't worry. It happens.
Yeah. See ya. It does happen. Okay. So we've got this equilibrium system, and there's cobalt tetrachloride, which is blue, and it's reacting with water to turn into cobalt hexahydrate, which is pink. And so there's a competition between the water and the chloride ions for this cobalt. So this whole equilibrium system is represented by this bottle, okay? What you're going to do, you just need to take a tiny 50 ml beaker, and you just need to pour out like a small amount, 20 mils or something. All you need is like this much in each test tube. That's all you need. This is maybe 5 milliliters. It's probably less than 5 milliliters, okay? So how many parts are there to part 1? There's a 1, what else? There's a 2, there's a 3, there's a 4, and then that's the end. So how many test tubes do you need? 4. You need 4 test tubes, if that's okay with you, okay? So you need 4 test tubes, and you're going to put this cobalt chloride and cobalt hydrate equilibrium in them. And then you're just going to very just qualitatively, no numbers involved, you don't have to take any measurements or anything like that, very qualitatively, you're going to perform these equilibrium shifts. So if I add water, what do you have to do to this? You add water. Are we okay with that? I was wondering how long it would take. Okay, so all we're going to do, we're going to take a little squirt bottle of distilled water. Sorry, sometimes it just fires, whatever. So we're going to take our squirt bottle of distilled water and we're just going to add a little bit of it. Is that okay? It's fine. But I didn't add it in there because I don't want to ruin the moment for you. So that's okay. So that's number 1. Now your evidence. Your evidence is what you see or what you observe. You know what I mean? So if I add water to this and it turns more pink, what's your evidence for adding water? Turned pink. Color change, turned pink. You know what I mean? You don't have to be, that's exactly what I would have written down had I been doing the lab. Right? Evidence for adding water, turned more pink. Or turned more blue, or whatever. Okay? So you're going to do that. So you're going to add some water. What are you going to do to your second test tube? You're going to add some silver nitrate. So you're going to find the little tiny bottle that says silver nitrate. Okay, spoiler alert. Silver nitrate. Does anybody know what's kind of special about silver nitrate? It stains your hands and your clothing. If you get silver nitrate on your hands or your clothes, it will turn your hands brown and it will turn your clothes black. Brown black. Okay? So, I'm suggesting, it's mandatory that you wear these, right? Very much mandatory. But if you want to wear an apron too, I wouldn't be opposed to that. Now what you're doing, you're taking a little dropper bottle, right? So you're taking a little squeeze bottle and you're putting 10 drops into a test tube. The odds of you getting it on your clothing, very, very, very slim. Odds of you getting it on your hand when you're opening up the squeeze bottle are pretty good. All you got to do, if you get some silver nitrate on your hands, what do you got to do? Just go wash it off, right? Okay, we're good. What are you going to do for number 3? Add heat. There's a buttload of hot plates out there. They're already on the counter because Miss Newton's period 1 class did the exact same lab as us, okay? So just between you and the labs beside you, right? Or the lab groups beside you, just get 1 beaker of water starting to heat up. As soon as you get out there, just start heating up the water, okay? You're just going to place your test tube. All you're going to do, place the test tube in a hot water bath. And it's going to change a certain color. And that's it, okay? And what are you going to do for number 4? You're going to have a beaker of ice water. And you're going to place the 4th test tube in the beaker of ice water. Is that okay? Now, that's all I'm going to mark. I'm going to mark those 4 things. I'm going to mark this, I'm going to mark that, I'm going to mark that, and I'm going to mark that, okay? Your analyses, again, you don't have to do them in the lab, right? For your analysis, describe the changes in concentration that would have occurred immediately, the direction the equilibrium shifted, and the changes in concentration that would have resulted from the shifting equilibrium. Is that not the exact same thing we've done 9 times already? Yes. Okay, so you should be very well prepared to do that, just as your analysis, right? Are we okay with that? Now, the part 2, if you have time, do this. Part 2 is thymol blue. This is just a tiny little squeeze bottle. Again, all you got to do is put this much of the thymol blue into a test tube, okay? And there's only 2 things I think you're doing. You're either adding hydrochloric acid or you're adding sodium hydroxide. the very last thing I want to say, any of the cobalt chloride stuff, any of this part 1 stuff, does not go down the drain. It is, I don't know if you can see from way back there, okay? The solvent, it's in ethanol. It's not dissolved in water. If you look back up at the chemical reaction, what's their state of matter? ALC, alcohol. It's dissolved in alcohol. It's dissolved in ethanol, right? Ethanol is flammable. It's also, like, some of you know this, it's really poisonous, okay? Then it's also, the cobalt hydrate complex is a potential, like, mutagen carcinogen. It's a health hazard. It can cause some health problems in the immediate future. It's probably not going to kill you, probably. And it's very dangerous for aquatic environments. It is not going down the sink. You understand that, right? There's a waste bottle out there, and you dump all of your cobalt chloride or cobalt hydrate stuff in the waste bottle. Good? 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 Good. Okay, we're at that second lab bench. Glasses first, then hot water baths. If you don't know who you're working with, let me know, and I'll help you find a group.